Hey physics, this is Mr. Hausman. We're going to be taking a look at one last idea having to do with forces on objects, using all the same forces we've been dealing with, but now what we're going to be looking at is something called inclined planes. In plain English, that's just a hill. So if we were to kind of emphasize that, inclined plane is nothing more than a situation where forces are on hills. And so what's different about this problem? Well, nothing really changes except for things get a little bit weird because of the hill. So let's talk about those. So let's talk about a skier or snowboarder here who's on a hill, and for now we don't know the angle of the hill, but let's call it angle theta. Now what does theta mean? It means if this was the horizon, right, how many degrees is the hill? So for argument's sake, we could make it be something like maybe 20 degrees. That's not very steep for now, but maybe you're on the beginner slope, okay? Now, one force that's acting on this person, because we always need to draw a free body diagram. Sorry about that, misspoke there. And what I mean is there's one force that never changes no matter what's going on, and that's the force of gravity. So what you do is from the person's center of gravity or the center of their mass is you continue to always draw that force first. And we should label that, and that's Fg. Now the problem with Fg is that it's not wrong to draw it that way. In fact, right, it's always toward the center of the earth, which is directly below you, no matter where you're standing on the earth. But the problem is that this person's motion is never going to be in the x and y axis if you draw them this way. That is to say, this skier is not going to be moving in the y axis, traditionally that's up and down on the page, or on the x axis, which is traditionally, right, the horizon, right, or the horizontal part of the page. So this skier doesn't move in either of those directions. So does it make sense to build an xy coordinate plane and try to find, kind of forces in those directions? And the answer is it really doesn't. Instead, what we're going to do is we're going to learn a technique. We're going to learn a technique where we rotate our page, and I'm going to try to do that now by rotating this whole picture. I think it's going to all stick together. Let's see if it does. And here's what I mean. Let's turn our problem. You can do this on your page. And so the technique first is draw force of gravity first, and then turn your page. Now, by doing this, all it does is redefine what is the x and y axis. And we're going to draw a dashed line to show the new x-axis. So right along the hill, we're going to call this the x. And now, where's the y-axis? Well, the y-axis is perpendicular to the hill, goes down here. We're going to call that y. Because snowboarders, skiers, any kind of animal or person sliding along a hill, they always move parallel to the hill. So the x-axis is almost always, in fact, let's say it as a rule, is the direction that the object moves. Either it could be pulled up a hill or it slides down a hill. So what that means is, or the next implication is that gravity is not really in the y-axis anymore. It used to be. But now gravity is on an angle. That's a little tricky. What angle is gravity on? Well, you notice that there's an angle here that gravity is making with the y-axis. And this gets a little bit interesting. But essentially, if we look at this triangle, the triangle that's formed by the hill, not necessarily meaning not any vector, but the triangle made by the slope of the hill and the gravity, you should recognize that this is a right triangle. That looks like it's perpendicular to the original horizon. And if this is a 20-degree hill, or if that's theta, that this angle up here in the corner, let's use black, is going to be 70 degrees, or 90 minus theta. In fact, let's kind of do that. Let's clean this up. And instead of, oops, I think we can do it. Yep, there we go. Get rid of that 20. Let's label that as 90 minus theta. You may remember from geometry that after the 90 has been established in one corner, the other two have to also add up to 90, so the total is 180. So if this is 90 minus theta, and you notice that the hill and the new y-axis are 90 degrees, is anyone seeing what's about to happen? Right here, this red angle is back to theta because it's 90, and if this side is 90 minus theta, then the missing angle must be theta. So a kind of a cool coincidence is that the angle of the hill is always the angle between the force of gravity and this new y. Okay, that should go in your notes. You'll just accept it, but that was the proof behind why it works. So the angle between the hill and the horizon is always the same as the angle between gravity and the new y-axis. Just a cool coincidence. Now, if the gravity vector is no longer in the y-axis, we are going to have to break the force of gravity into two components. So your notes may be both a mixture of ideas as well as pictures. And what would we call that? Well, that is part of the force of gravity, right? But it's now the force of gravity that's parallel to the hill, and we would call that force of gravity x. There's also a component of the gravity, right? That's the gravity that pulls you down the hill. And then here's the component of gravity, let's put an arrowhead on it, that we would call FGY. This is the part of the gravity that pulls you into the hill. So when you're snowboarding, hiking, skiing, anytime you're on a hill, doesn't gravity tend to pull you down the hill, but also it pulls you into the hill at the same time. And depending on how steep it is, may determine like which force is bigger, okay? Now, let's see other forces that may be present. Well, we will very quickly be adding in the force of friction, and force of friction is always opposite the way that you are moving. So if you're sliding down the hill, the friction will be against you. However, if you're being pulled up the hill, maybe by a rope tow, or you're at the beginner slope of a snowboarding mountain, the force of friction could be down the hill. We'll keep it simple for now. Now, it leaves us with one force that we should be looking for, but we haven't drawn in yet, and that's the normal force. And if you remember, normal means a surface like the hill pushing up on the skier. But normal as an adjective means that it's actually perpendicular to the hill. It's no longer opposite gravity. In fact, it's opposite the force gravity y, right? So force and normal and the force gravity y are both vertical forces, right? They're in the y-axis. And in this case, force gravity x and the force of friction are both in the x direction. So it's just a new way to orient your free body diagram. Now, is there a way to calculate these forces? Absolutely. So how do you find the force of gravity? That's still mg. And how do you find your forces of gravity? Let's use some trig in this triangle. Well, the force gravity x is opposite the angle we know. So anytime you're solving for the opposite side, you use sine. So force gravity x will always be sine of theta, the angle of the hill, times the hypotenuse. And what is that hypotenuse again? The hypotenuse is actually the force of gravity. So essentially, it's m times g. Now, if you've already calculated the force of gravity, you could also say that it equals sine of theta times fg. Next up is fgy. And what side of the triangle is that? You should recognize that as the adjacent side. We'll put a little a there. This was O for opposite. So if you're trying to solve for adjacent side, we're talking about cosine of theta times mg, or cos theta times fg, meaning the same thing, right? Fg is still, how do you find that, is m times g. So that's kind of a free body diagram setup. And we're going to now do a practice problem together. So you have one that you can reference going forward. Okay, sample problem number 1. If you're noticing where we are, we're actually on page 19 in your packet. That's actually going back a few pages. We had already done friction problems, but that's where free body diagrams or inclined planes are introduced. So quick reminder, we just have, we're on page 19. Okay. There we go. Let's write that a little darker. Okay, nice. So what this problem is describing is it's kind of nicknamed the evil slide of doom. It's so steep. It's maybe at one of those water parks where you're coming down the hill so steep it feels like you're almost going to fall off the hill. Now I can tell you that this is no different than at a 10-degree hill, 20-degree hill, very low angles. 85 degrees just creates a small problem. Here's what I mean. It is so steep that it's hard to accurately draw the forces. It gets a little weird. But we learned on the previous slide that the step one is to draw in the force of gravity, right? And even maybe put mg next to it, right? That's how you find the force of gravity. That's my best vertical line for now. But remember, he's never going to move in that direction. His motion is entirely in the x-axis. So we're going to put in a dashed line and say this is the x-axis, and this is the hard part, but you have to kind of imagine that this is the y-axis. So what really helps with this is if you twist your paper and you turn your whole paper, and now we've drawn the force of gravity, but we've reoriented the problem so that it's on the x and y axis. Okay, so let's put in some colors to kind of map out some forces. So we talked about how the force of gravity has to be split into an x and y component. And it was actually a student in 5th period. He's kind of insightful this way. Happens to be a guy named Alex. You probably know him. And Alex said, I don't draw the vertical, the y force first. I always draw in the x force because gravity is parallel to the hill. And your brain can kind of say, well, that's parallel to the hill. So that must be the force of gravity that's parallel to the hill. So he draws that first. How far does he go back? He goes back to where the y-axis would be. Now let's label that. That's force of gravity, but it's parallel to the x-axis, so it's kind of extreme and hard to see, but that's your force gravity, x. Now, the reason why he does that force first is because then when he draws his force of gravity in the y-axis, he knows exactly how long to make it, FGY. And that's helped a lot of people. So you're learning that trick early on. I never thought of that. I usually draw FGY first, then FGX. He's kind of saw this cool trick. Okay, while we're here, we're going to draw in any other x and y forces. And as it turns out, the only other y force, right, is the normal force. And again, it's the hill pushing out on him perpendicular to the surface. And these two forces, even though we haven't calculated them yet, are equal and opposite to each other. Okay? Now, this problem is without friction, so it looks like the only force that's left, right? There's no friction up the hill. The only other force is FGX. Now, a lot of people say you can't possibly calculate FGX if you don't know its mass. If you reread the question, it's an evil slide of doom. There's no friction. What is the acceleration? It's just an 85-degree hill. Well, as it turns out, you don't need the mass. And let's see if we can figure out why. So humor me while I turn the problem back, and I'm going to actually reduce its size, and now we have a little room to work here. It'd be pretty cool to be able to do this in an everyday problem. Let's go to a white pen so we can see it better. Okay, so step one. We drew in the force of gravity, right, on the system. So let's write you FG and the FBD, right? We draw it. Step two is we twisted, right, our x and y axis. I drew in my axis, and that allows us to draw our FGX and our FGY. We call those, of course, component vectors. And what we're doing is, this is weird, but we're breaking gravity into the two directions it pulls, parallel to the hill and perpendicular to the hill. Now, we know, right, that once you've drawn a free body diagram, you should really calculate, right, all of your forces, right? Let's put some numbers to them. And in this case, we only have FGX. So how would you calculate FGX? Well, you don't have mass, but you know that it's opposite the 85-degree angle. So it would be sine of 85 degrees multiplied by the weight of this object. And we don't know that weight or the force of gravity, but it's mg. We can write an expression that gets us there. And that's the only force that's accelerating the system down the hill, right? It's the only force that's parallel to the acceleration. So next step is to use Newton's second law. right? Step 5 is to figure out the sum of the forces that are parallel to the acceleration. And in fact, isn't it the sum of the forces parallel to the acceleration divided by the mass gives you the A? Well, I'm going to flip that around and rewrite it like this. Sum of the forces over mass. And if I substitute in, let's go to a color that we can see. Hopefully, I think white will stay with. My fault, there's not many other choices, is we have a force that is the force of gravity, x, so that's sine of 85, multiplied by mg, then divide that by mass, right? We just plugged in an expression for the only force that's parallel, and the masses cancel out, so you suddenly realize that the acceleration is the sine of the angle, 85 degrees, multiplied by 9.8 meters per second squared, the g value, the acceleration due to gravity. Now, when you do that out, you're going to find out that A is, I believe, 9.7 meters per second squared. Now, it's parallel to the hill. It's going down the hill. You could say that down the hill is negative 9.7, but of course, that is how you define your x-axis. So either way, the acceleration is 9.7, and it is a direction that is down the hill. Okay, so that's kind of an introduction. I know that's kind of a sample problem in a basic. I told you this wasn't going to be a totally new way of thinking, but the key thing here that's brand new is drawing your gravity x and y components and then doing new calculations with those. So let's see how we do tomorrow when we try this in class. Thanks for watching.